That should be the front of the LiDAR, I think, Monty? Yep, I see Monty walking around. You guys see Monty?
That's me. This is my hand.
Yep. Oh, that's me sitting over here. Okay. There's Monty. Come on, you guys. Put the right side up, the left. Get closer, have fun. Look, robotics is a hands-on interactive sport. Let me find, hey, chat is here. Can anyone hear anything? You have no audio.
This
Join
LiDAR
audio.
is a sensor we use on the robot.
Let's see. Can you guys,
Or cars.
I'm here now, out in Zoom land. Yes, sir. Oh, man, there's so many things working. It's got to crash. So this is a LiDAR. LiDAR is laser ranging device. Or, you have radar, which is an acronym. LiDAR is not exactly an acronym. Somebody said, oh, it's like a light radar, so they called it LiDAR, okay? But it's a light ranging
Light
device.
detection and ranging.
There we go.
Right.
See, that's why I want some color commentary from Mani. So this one is a 16-beam Velodyne. And if you come up here and touch it, which you're welcome to do, you'll feel it spinning. So this is not a solid-state LiDAR. There's actually lasers on a cylinder, 16 of them. I don't have 16 things to point, so I need 6 more, but I got 10. That's not bad. And it's spinning on its axis. What we use on my Cassie robot is 32 beams, but there are cars that have 128s on them, so 128 lasers spinning around, okay? So what is the LiDAR doing? It's sending out a pulse, a laser little pulse, and it's reflecting off of Mani, for example, and it comes back, and it measures the amount of time. That's called time of flight. Now, you guys know the speed of light, c, okay? So the light has traveled twice the distance to Mani, so you know the speed of light, you know the time, you calculate the distance, you divide by 2, that's Mani's true distance from the LiDAR. Okay, so that's the first thing to understand. It's got all these beams, and it's returning X, Y, Z coordinates of everything the LiDAR reflects off of. So you can imagine that's pretty powerful information for letting a robot understand where it is in its environment. So that's the first thing that's cool. This coloring, it's a little bit artificial. I mean, the LiDAR can also measure the intensity of the light that comes back. If it's bouncing off of certain things, a lot of the light gets absorbed, and so that's less intensity. Okay. So these images, sometimes people color them according to distance, but this one, I believe, is being colored according to the intensity of the light as it reflects off. So if we had a sheet of aluminum foil, we could get some super intense light here, okay? Mani, do you have a mirror that you use?
Yeah, my pants are black. Where am I? You see a difference?
He looks like he's in a clown suit, doesn't he?
Yeah.
With the stripes.
That's not who I am.
That has nothing to do with your true profession. Is that what you're saying?
I'm not as funny as a clown. So
what it's doing is the more intense, the darker the color, which is weird. Okay.
So I think when the light is getting absorbed, it's we see yellow color, right?
Yeah.
And when it's reflective, we see yellow, green, yellow.
So.
And when it's observed, it's usually darker.
Oh, I see what was happening, Monty. I think you had they were all reflecting up to the ceiling, And now I make it normal.
Well, the angle is important when the
Yeah.
light is hitting the
Yeah,
object.
because if the light can come in and
Yeah.
just bounce off, not going to see it.
But generally, the intensity from LiDAR is negatively correlated with cameras.
Yeah.
That's a mouthful, but
Now,
in computer vision, of course.
look, you guys have a relative idea of the spatial orientation of the room with respect to what you're seeing up there? Okay. What just happened?
The room moved.
The room moved, right? It looked like the room moved. That's not fair, right? I mean, I want to get this data and I want to understand where I am in this thing. And sorry,
So today we're going to talk about the special relativity.
today we're going to have a lecture. And here would be the room, 180 degrees backwards, okay? So what's the point here? So I do this. We'll let it settle. So this is usually mounted on a car or a robot that is mobile. So if it's Cassie or Digit, it's sitting like up here, right? And it's on the head. And as I'm moving around, look, is the room shaking up and down? So the room is shaking, right? No. This device is moving. The room is fixed. Okay, so we're going to give you guys LiDAR data, but you have to understand, the sensor measures with respect to its own coordinate system. So it has an x-axis that goes out here, it has a y-axis, and then you do the x into the y, so the z is pointing down. That's just the way they've done the coordinate system on the sensor, okay? But when Cassie turns, the world turns. No. If you want your image with respect to a fixed coordinate system, you may go out to the atrium and the stage and just say, hey, that's my reference, okay? I'm going to put an XYZ coordinate system on the stage, and we call that a world frame. It's our reference frame, okay? And if you want the room to always be, let's see, that's south, north, always east of the stage, then you need to put these images that are coming off the LiDAR in the coordinates of the stage. Okay. Now what we often do in robots is, because we don't really care, we'll just start up the robot, let it be still, and we'll take that as the initial frame, and then we'll take all of the motion that takes place, measure that motion with respect to the original position and orientation, and then transform everything back to that common frame. So that's a pretty common thing to do, I would say. What do you think, Mani, about that statement?
Yeah, it's also an ongoing research still in robotics. This estimating or finding out what are these transformations as we move, orientation and position, and putting them in the common frame to have a reconstruction of this room that looks like what we see. That's a very difficult task. And if we can do that, we can build maps, we can localize.
Yeah, so what we do on our robots is we have this LiDAR device, we might have a camera too, but we'll put something called an inertial measurement unit, and it has two types of measurements. One is it measures the acceleration in x, y, and z. Okay, so if you take acceleration, and if you had a little bit of calculus, you integrate and you get velocity, and then if you integrate velocity, you get position. So we have filters, algorithms, it's called a Kalman filter, that takes the acceleration data, tries to compensate for little small errors that IMU makes, and it gives you the XYZ displacement of Cassie, mini cheetah for Monty's robot, or digit, or the autonomous vehicles that are going up and down the roads that you see all the time. So that gives you the XYZ, and you know the position of the LiDAR with respect to how the inertial measurement unit is getting, so then you can get the translation, okay, because the robot can translate, okay? So the sensor is a 3-vector, yep. It's measuring in its coordinate system, and we have to take the data in its coordinate system and move it back through the IMU measurements to some fixed coordinate system so that we can build our map with respect to that. Mon, you want to pass the mic so we can get the question and everybody will hear it?
Are we going to learn how to implement a Kalman filter by any chance? Because I've tried working with this before, and actually, I mean, this is part of some of the research that I'm doing, and working with a not too expensive IMU, it was very hard for me to double integrate to position because of like how much noise there was, and all the numbers would just go crazy. So I was just wondering if we're going to like learn anything more about that.
No, we don't do that in Rob. So the question was, are we going to build one of these filters that takes the data from this inertial measurement unit, which is acceleration? So you have position, then the rate of change of position is velocity, and rate of change of velocity is acceleration, and then you try to go backwards. We don't do that in Rob 101. They talk about it a little bit in Rob 103 that we were teaching, which is equivalent to Engine 100. And so when you and Katie do the sensing course, will there be IMUs in that at all? Yes. So that's 320, is it?
That will be a 300 robotics course. We will teach IMU and motion tracking. Yeah. And then later there will be I think this winter we will have 400 probabilistic robotics. That is in parallel with Rob 530, which that's the graduate course I teach. Yeah, so it's Kalman filter. You guys are maybe not quite ready to jump in that, but man, the courses are coming so that you can get in them. So great question, and no, we don't do it because we don't assume calculus and differential equations, which we would need. Okay, so that's the translation. The inertial measurement unit also measures the rate of rotation about roughly the x-axis, the y-axis, and the z-axis. Okay? We have gyro in our ear. Yeah. We can. You have a vestibular system, and if you spin yourself around and you get yourself all messed up and your vestibular system becomes uncalibrated, you just fall to the floor, okay? Your vestibular system helps you know what direction is up, and that's how we try to keep ourselves upright, okay? So attached to the IMU is getting the angular rates about these axes, and similar to how you take acceleration and you go backwards to velocity, then you go backwards to position, you take angular rates and you go back to angles, and then we keep track of how this thing rotates and moves. And so when we do project one, I'm going to give you the conceptual part when Monty gets his computer hooked up there. I gave you some slides on Slack. This is Damon's computer. I mean, I can get mine out if you want. Oh, my computer is there. Yeah. We're going to give you the transformations, and we're going to take you through the process of how, though, you use those transformations to take first two vectors and move them around. So we call that R2 when there's just an X and a Y component. And once you get good at that, then we're going to give you 98 megabytes of LiDAR data and have you what's called register that data, transform it all back to a common XYZ coordinate system, and then you'll build a GIF of Cassie walking on the grove. You ready for it? Question? What do you do about shadows in your LiDAR?
I noticed when you're walking around it, you're in the way the lasers have shadow. Yep, so question was, what do we do with shadows? That means, what are we doing with obstructed views? And this is definitely a problem. You're trying to see a pedestrian, but there's a car in between. You just can't. So it's the same problem that we have as humans, and you try to take advantage of your relative motion to be able to see what's going on with the next, by having multiple scans and comparing your relative motion to those things, and eventually you probably uncover the obstacles.
Connect both at the same time.
Really? Oh. Anybody want to come up and just touch the LiDAR? Come on. It's not like every class you get to do it, if we were doing something else, we'd just pass it around, but here it's hooked up. It's warm, it's burning energy in the car. You can feel it rotate, just put your hands on it.
Oh, we got both.
Yep. Mani is getting things set up so I can explain exactly what you're doing in your project. There's now these things called solid-state LiDARs, which don't have any moving parts. It's basically a panel of laser beams on the similar technology as modern TVs, okay? And they're supposed to be more robust, et cetera. We have some good questions on the chat? No, they just couldn't see us, but we got that. And they're saying the screen looked weird. Yep, that's when we had reflections. The 128 beam LiDARs, man, you get this super dense image, but this one is like, I don't know, this one's probably $4,000 or $5,000. The 16 beam, 32 beam is $5,000 or $6,000. The 128 is probably $20,000 or something.
I think, yeah, $15,000 to $30,000 usually.
Yeah.
The ones that we put on the robot. It's very expensive. That's why you read on news that a lot of people try to use cameras for cars. But it's very accurate. And in the future, the cost probably will go down and more people will use it.
Yeah, so now what we're sending to the people out in Zoom land is different than what we're sending to the classroom.
Yeah, and Zoom, they see LiDAR point cloud.
Yeah, so I guess we stop share and then maybe...
I can switch camera, but
that's cool. Switch camera, that's a new feature. That's a good feature.
But
yeah.
I need to...
Switch camera, that was good, right?
Yeah, they can see it,
yeah.
but it's not exactly the projection.
It's not the projection.
Yeah.
I don't know. You want to adjust?
We can just cut off the other one.
Yeah, I think we can just do that. So here's the connector. And we'll start share again. Oh, we're all good. You guys want the lights back up, or you like this? Okay, now we got one screen off, one screen on.
Some people fall asleep.
There we go.
If it's too dark.
Okay. So here's what you need to imagine. We're just going to have one object for our LiDAR, but of course you saw all those returns. There's like 10,000 returns, okay, from those things, okay? We're going to pretend there's only one return, but you guys will use a for loop to handle the 10,000, okay? So it's not like you have to write down 10,000 times the transformation. That's why we teach you for loops. So here's the thing. We have these coordinates, which are actually the real thing we're calling our world frame. We're building our map with respect to this. This is the origin, and it's 0. And then we have this object, which I've drawn kind of like a house, and here's its true x, y coordinates. But as we were talking, the LiDAR moves. LiDAR's on Cassie. Cassie measures in the LiDAR coordinates that the house is xc prime, yc prime. Okay? But thanks to this IMU, we're keeping track of where Cassie is. So once we have the points from the LiDAR, how do we take them back to the world frame?
You add so I'm trying to use values of how much you moved away from the origin.
So what was proposed is we take the measurements that Cassie is given, the LiDAR on Cassie is giving us, and then because we've kept track of where the LiDAR is relative to the true world frame, we just add those two numbers together and we have the correct position. And that is exactly 100% right, okay? So you just add the offset. Linear algebra, okay? For two vectors, you do the same thing if it's three, x, y, z. So if Cassie were moving up a hill, etc. So that's the easy part. So here's the house once again, but now Cassie has turned, and Cassie reports back that the position of the house now is xc prime and yc prime. Those numbers look very different than xc and yc, the true position of the house. So how do I take this measurement and get it over here in this frame? How do I do that?
It's all about the right attitude. If you know your direction that you're heading, you can adjust your attitude. We need to align ourselves, I think, with the world frame, right? If x prime is pointing in the same direction as x, then maybe we have a chance of just adding them like before.
So the object has been rotated. So in Rob 101, matrices for us are things like AX equals B. But matrices have another role of transforming vectors from one coordinate system to another coordinate system. That's another aspect of matrices. And Project 1 is going to take you through a tutorial with planar objects like these to let you understand how rotation matrices, you'll work on something simple, a diamond, you'll move it around and you'll rotate it, so you do translations and rotations. So the true measurements, as a function of what the LiDAR says, is you need to operate on them to recover by something called a rotation matrix. And that's provided by the IMU, just like the IMU provided the translation. So what we're going to do is teach you something that roboticists use that's called homogeneous coordinates. I guess there must be heterogeneous coordinates too, right, Bonnie?
We never heard of that.
We got to have them, okay. But they're special coordinates such that if you use these coordinates, you can combine the operations of translation and rotation into one super matrix and just take care of rotations and translations all with one single matrix operation. So that's going to blow your mind a little bit when you're wrapping your head around homogeneous coordinates. But this is how complicated it is to form a homogeneous coordinate. I have my x, I have my y, maybe I have a z, maybe I don't, depending on R2, R3. I add a 1 at the bottom. I think you guys can handle that, right? So going from xyz to xyz1, that's called creating homogeneous coordinates. It seems totally stupid. Something that's stupid, could it possibly be useful, Mani?
I think then it makes sense to multiply matrices with that vector. That's why it makes it easy to use, but conceptually, it's very difficult to
so it's going to seem like that's just like totally brain dead, and you're going to see it allows you to do translation as if it's a matrix multiplication operation. It's not, it's addition. We're going to turn addition into multiplication. And since rotation is a multiplication, we now have both operations in the same form, and that makes our for loop super nice. And so the IMU is giving us the rotation and the translation part. We stack them up appropriately, make this bigger matrix for homogeneous coordinates, and you take your data and you're rotating it as the robot is walking, and we're building these beautiful maps.
Yeah. By the way, if somebody likes aerospace engineering or flying robots, they use similar algorithms to estimate the orientation. It's called attitude estimation problem. Then the robot can do maneuvers of like flipping in the air, but ground robots use similar algorithms too, plus having contact with the ground.
Yeah, so once again, what we're going to give you are the measurements in the IMU frame, and we're going to give you the transformation that takes it back to the world frame. So we're giving you a lot. But this is what you get from the LiDAR. Measurements in the frame of coordinates. As the robot moves, the world moves, no. It's the representation. You have to take those coordinates back. And project one is doing these coordinate transformations. So that's the idea. Questions, or ready to do LU factorizations?
Yeah, I think we can start LU. And are we covering linear transformation in lectures or in the lab? We have some notes.
I think they're covering it in the project, and then we'll help you as much as you need in the recitations as well.
I think Trippy will teach you. We have some notes. You can learn from those.
Let's see. All I need to do is get this out of your way. I'll turn this off so it doesn't drive the students crazy.
Should I teach like this today? I'm going to sing LU factorization for you. I want to dedicate this song to last year's students who took the course for the first time.
I don't know. Where's the canvas here? We like to move around. We're super smart, but we try not to intimidate everybody. Be scared as they walk by, frightened as they walk by.
Should we start LU? Oh, it's not. Okay, now it's on. All right, so let me change my slides. So we are going to talk about LU factorization. Now, this topic, it takes a little longer to cover different variations of it. So today we will talk about the basic version of LU factorization. And hopefully next time we will talk about a more advanced version of it that has row permutation. And that will give us some more time to solve more examples as well. Okay. Now, so far, we learned how to write down a system of linear equations into the matrix form when we see it. We also learned that if the system is of the lower triangular form or upper triangular form, we can solve it using forward substitution and backward substitution, respectively. But what we didn't learn is that how can we get those lower and upper triangular matrices to begin with? Because it sounds like if we have them, the problem is solved after you implement your forward and backward substitution functions in the lab session. But the problem is getting those matrices, and that's usually the hardest part. So today we learn how to reduce a hard problem into two much easier problems. And that's the LU factorization. But the concept of factoring a matrix into the product of two matrices, or there are other versions, maybe three matrices, is a topic that, well, we have a matrix, we factor or decompose the matrix into product of multiple matrices. We will learn LU later in the course. We will learn QR. That's another version that is very, very important and common. We use in practice QR a lot. So when you hear that, so that's the topic of factorization and factoring a matrix. When you hear matrix decomposition or factorization, they usually mean the same thing. And it means splitting the matrix into several matrices. Now, the example that we go through, it's really an algorithmic way of calculating LU. The traditional way of teaching LU is a little different. But what you see in the book that Jesse wrote, that's maybe somewhat more obscure in the traditional courses, but it's more exciting. And so actually, I find it easier to learn. And permutation is this next time, okay? Now, before learning LU factorization, we need to learn a second way of multiplying matrices. So the standard way was multiplying each row of the first matrix by each columns of the second matrix. And that would generate each entry of the resultant matrix. Now consider A to be a 2 by 3 matrix here. B is 2 by 2. Instead of partitioning A into rows, let's partition A into columns. And instead of partitioning B into columns, let's partition it into rows. We're completely reversing the order of using row and column partitioning. Now, what happens if we take these rows and columns here, and instead write down first column of A multiplied by first row of B, and second column of A multiplied by the second column of B. That looks like a strange thing to do because it doesn't look like that vector-vector multiplication that we learned. So we see that the columns of A, they have the dimensionality of 3 by 1. It's a column 3 vector. Rows of B are row 2 vector. When you multiply them, right, you have A 3 by 1, B 1 by 2. Does the multiplication make sense, first of all? Can we do this? So there's no problem with the syntax, right? Because the number of columns agree. Columns of the first one agrees with the number of rows of the second one, both 1. And this should give us, let's say, a 3 by 2 matrix. Okay? So we're not going to get any error. We can do it. So let's try and see what happens when we do this. So we calculate the first one, the first column of A, multiplied by the first row of B. Column, row. We get 1 times 3, right? 1 times 4, And now we have the first row. 3 times 3, 3 times 4. We have the second row. This is the same rule as matrix multiplication we discussed last time. Now we have 5 times 3 and 5 times 4. We get the third row. Third row, right. Now we do the arithmetics and we have a 3 by 2 matrix. We can do the same thing for the second column of A and second row of B. And we get another 3 by 2 matrix. So we can, mechanics of the problem, it's consistent with what we learned. And it's possible to calculate this. Now when we add them up, we get the same thing as A times B. That's the magic of the second way of multiplying matrices. What just happened? You can try it in Julia. Get A and B, multiply A and B, or say the first column of A multiplied by the first row of B plus the second column of A multiplied by the second row of B. You get exactly the same answer. And by the way, the reason we write 1 column 1, because if you don't do that, Julia will return a column vector by default. It takes the row and gives you a column vector. But when you do this, it gives you a row. All right, so it is possible, although you're probably not convinced why. So in general, what happens, instead of summing over row times columns, instead of, calculating rows times columns, if you remember last time we had a giant matrix and each of them was a sum. Sum over multiplying row elements of a particular row of A times elements of the column of B. But it turns out we can have a sum and then do column by row multiplication. Now this really will make sense to you when you build an image of column space of a matrix. We are not talking about vector spaces yet. And I think it suffices to learn how to do the calculations for now. But a column space of a matrix, that means when you think of a matrix as columns, instead of thinking about it as rows, it gives you a very different meaning. And that's usually a very powerful image to build when you increase the number of dimensions. So what we are doing, as if we are taking each column of A and weighting it by each row of B and summing them up, right? As if these were some individual elements, each column, and we could weight them and add them up, and by doing that, we could just manipulate it somehow to get the output we want by just weighting each column and summing them up. So that's the reason it's happening, and in the lecture about vector spaces, I think that's one true reason why we can do this. Because imagine B had one just row, right? what would happen? So if k is 1, right, we can directly get this idea in our mind that we just take the columns and weight it for each element in the row of B, and that it seems like weighting them and adding them up will give us some results. So I'm not going to make it more abstract now, and I wait until future lectures to talk about vector spaces. But that's a very different image to build from looking into matrices. But this gives you a second way of multiplying matrices. And it works just as well as the first method that we learned. Do you have questions so far?
So I guess there's a difference, right, between doing column vector and row vector multiplication versus like an n by k matrix times, or sorry, an n by 1 matrix times a 1 by m matrix. Like because didn't we learn that in order to do column vector times row vector multiplication, they have to be the same length?
Right. What we learned was that we have 1, 2, right? And then the other one is maybe 3, 4, right? And we said that, okay, if this is 2 by 1, the other one must be, sorry, if this is 1 by 2, the other one must be 2 by 1. And this will give us 1 times 3 plus 2 times 4. 3 plus 8, right? 11.
And so that's different than doing, so if let's say it was then 1, like a 1 by 2 and then a 2 by 3.
If it's 1, 2, right?
Yeah.
3, 4. 2 by 1, 1 by 2.
That's the same thing, right?
No, it is
Oh, because the column is first?
100% different. Because we get, if you do matrix multiplication, we get 3, 4, 6, 8.
So how do you differentiate between, if the matrices only have 1 row or column, like how do you differentiate between vector multiplication and matrix multiplication?
Now the question is, how do we differentiate between matrix multiplication and vector multiplication? Because one is giving us a scalar. The first one is giving us a scalar. The second one is giving us a 2 by 2 matrix. Like clearly, these are not the same thing. We're not doing the same thing. And the simple answer is that I'm not really thinking about it when I'm calculating. But if you give me this row and column, by just following the rules of matrix multiplication, I get these answers, right? So it's possible there is no syntax problem, because what must agree here, it agrees, right? Now, again, when we learn vector spaces, the first one is the dot product one of you brought up last time, right? The second one, it has a name. It's called outer product, but it's not really 2t or 1t, something like this. But it's a little out of scope of what we want to talk about. So one, the dot product, another name for it is inner product. One is collapsing it into a scalar. The other one is expanding it into a matrix. These are two completely different operations. That it's just possible to do it by the way we define vectors and matrix multiplication. They do not mean the same thing.
How do you know which one you're supposed to do? Like if you were just given either one of those, how do you know if you're supposed to do the inner or the outer?
Now, we define a first method, right, for matrix multiplication that uses this form, right? And then we learn a second method today, just the definition of it, that it uses this method to calculate matrix multiplication. Now, clearly, there should be a relationship between these two because that's your question, because we get the same answer. Then what is the relationship, right?
Well, I was just wondering, like, how do you know, is there a reason, like, because the row becomes, like in the first example, the row vector comes before the column vector, right?
Mm-hmm.
So does that imply that it's vector multiplication, and then because the column is before the row in the second, does that imply that it's matrix? I'm just confused as, like, if you were just given one of those and you weren't told whether it was matrix multiplication or vector multiplication, like, how would you know?
Oh, you're worried that I give you two arrays and you're not sure if it's a vector multiplication or matrix multiplication. You don't need to be worried about that because the operation of matrix multiplication I'm doing here is exactly the same thing. It's just the dimensions are different. Well, because the sizes are different, right? The one is 1 by 2 times 2 by 1. By definition of matrix multiplication, the result must be 1 by 1. The other one is 2 by 1 times 1 by 2. We expect the output to be 2 by 2. Now, we never said in this course that column vectors and row vectors are the same. We differentiate between numbers that are in the column and rows, right? So because of that, we just follow the rules. You don't need to think about it. Just follow the matrix multiplication rules and it will work out. Okay? So in fact, when I wrote this Julia example, I am using the same operator that multiplies matrices. It's just vectors are in rows and arrays. So we will try to build a better geometric image of this in future lectures, in vector spaces and least squares problems. But why do we need this second method of multiplication? Is it just another way of doing the same thing? It is, but it turns out for LU factorization, this second way of doing it is a very natural way to decompose matrix algorithmically into a lower and upper triangular matrices. It's called iteratively. Through some steps, iterations, we can calculate something, use the output for the next step, and recalculate something else, and then we get the desired outcome after a few steps. Now consider A and B. So A is clearly a lower triangular matrix based on what we learned so far. It is 2 by 2, and every element above the diagonal, this was your diagonal, is 0. B is upper triangular. We have a triangle in the upper part that includes the diagonal as well. Every element below the diagonal is 0. What happens if we multiply A and B? Now, we get a matrix that looks just like any other innocent matrix. 5, 2, 15, 2. What we want to do, we want to go backward, right? If I give you this matrix, the result of A times B, can you give me A and B? That's the question, right? So we are after a process that take us back from the matrix, gives us lower and upper triangular matrices. Is the problem clear for everybody what we're after? Okay, so the problem is defined now, and we want to learn how to do it. We learned about partitioning matrices. Let's partition A into 2 columns. So we have.
So is every matrix a multiplication
question is every matrix multiplication of a lower and upper triangular matrix. For now, I'm going to say no. So LU, what we're talking about non-singular matrices, first of all. We're talking about square non-singular matrices, matrices that are square and the determinant is not 0, okay? Because we already know that we're going to be in trouble solving the linear system if the determinant is 0. Which this algorithm, by the way, we will give you a hint why this happens. But let's limit the discussion to square non-singular matrix. The matrix is singular if the determinant is 0. Okay? There are generalizations for other methods. But I think we decided to just go with QR later. When it's rectangular, we just use QR factorization. That's more straightforward. Okay? But a stronger answer to your question is that if it's possible by exchanging rows of the matrix, right, to solve the linear system, LU factorization with permutation will find that, right? It will always find that. So row permutation is a necessary and sufficient condition for getting that. So there is no way that LU cannot find that if you have a square matrix and by just exchanging rows, right, you can get it done. So it's very powerful in that sense, and it's very preferred when you're solving square linear systems. I hope this is a little reassuring why LU is important. But our conversation here is limited to square, again, non-singular matrices. All right, so partitioning in, remember this was definition. I'm defining C1 and C2 here. C1 is the first column, C2 is the second column. We talked about this in the previous lectures. And I am going to partition B into rows. First row is R1. I'm defining again here. And the second row is R2. Okay? So far, straightforward, whatever we were doing before. Now, how about we'll write down the matrix multiplication of A and B based on what we just learned. The idea was that the first column times the first row, right, the second matrix, plus the second column of the first matrix times the second row of the second matrix. So that will give us C1 times R1 plus C2 times R2. And let's just verify that if we define C1 and C2, you can stack them in a row to get A. You can define R1 and R2 here, and then you can stack them vertically. So here I'm stacking horizontally. Here, using semicolon, I'm stacking vertically. So very different operations, but we can use columns and rows to do that too. So we construct A and B. So A times B minus C times R1 plus C2 times R2 must be equal. So if you subtract one from the others, we should get 0, and we get 0. It is just two different ways of matrix multiplication. That's just the test. Now let's go through the process of factorizing this matrix M into a lower and upper triangular matrix based on what we learned so far. M is just an ordinary matrix. It's non-singular. Step 1. I'm using K to count the steps, right? Step 1, K is 1. This is computer scientists do this. Or when you prove something by induction, you use this. K is 1, K is 2, K is n plus 1. Step 1, define C1 and R1 to be the first column of A and first row of A. So obviously this is going to be C1. This is going to be, so LU is not that easy. You might make mistakes. C1. English is not my first language. Sometimes I confuse columns and rows. I don't. I'm justifying my mistakes. Okay, so hopefully this part is easy for you. You just look at it and you say, okay, this is the first row, this is the first column. We need to learn a new concept, and that's called pivoting. Whenever you define the column, at step K, find the element on the diagonal of the matrix, K, right? K is 1, so we're talking about 1 and 1, right? Which is 2. Next time we will change. Call that variable pivot. And divide C1 by pivot to normalize the first element. So that makes, assuming the pivot is not 0, right? We don't have division by 0. That will make the first element, or the kth element row of the column we're working with, makes it 1. Okay? When I write the general formulation, you will see why we do that. Otherwise, it's going to have double counting. So we have to do this normalization. So we define the pivot, divide the column, normalize it, and don't do anything with the row.
If the pivot wasn't a clean number, let's say it was 3 in this case, would we just use the float, would we actually just convert it to floats and things like that? Or would we use the decimal?
If the pivot was a floating point number.
Well, I'm saying if instead of it being a 2, let's say it was 3, so 4.
Oh. If it was a rational number, right? If it wasn't as easy as 2 divided by 2. Yeah, the computer will do that for us, right?
I just didn't know if we were forced to
Yeah, ultimately, this is about the scalability. We try to find the algorithm. We're not going to do it by hand. Yeah, so it's just a bunch of numbers divided by the pivot. Pivot is non-zero, and that whatever that might be. Okay? Now, your question has a deeper answer that, well, computer is tracking up to 15 or 32 numerical resolution accuracy, right? We keep dividing. What if we lose accuracy by cutting off whatever comes after 15, right? That, for certain matrices, that can be a problem. So algorithms are not equal in their numerical stability ranking, right? Some algorithms are maybe good by hand calculation, some are good for computers when they do this sort of numerical calculations. QR algorithm that we will learn is very stable numerically, the version that we use. Yeah.
So I'm wondering the difference between the column,
those two.
What's the difference between those two? Which two?
I mean, when the colon is right or the colon left, like the notation.
You're talking about 1, 2?
No, like inside the rectangle, like pivot.
Oh, you're talking about here?
Yes.
I'm just defining pivot. So I'm saying pivot is a name for the variable. You call it P. I'm calling it a bit longer, pivot. I'm going to define pivot to be M, K, K. And K is 1, so that's going to be 1, 1. What is the number on the first row and the first column of M? This is M. 2, right? So let the pivot be 2 in this iteration. K equals 1.
When the colon's on the other side, it's just like the reverse representation.
Yeah, and I'm saying that assign C1 to be the first column divided by the pivot, which makes it 2 divided by 2, 4 divided by 2, 6 divided by 2. This will give us 1, 2, 3. Does that make sense? Okay, so I'm taking the first column, dividing it by the pivot, and pivot comes from the diagonal element based on value of k. And do nothing with the row. Just keep the original row. Okay, once you've done that, subtract C1 times R1. C1, remember, was normalized by the pivot. What will happen that you see a pattern here. We could zero out the first row and the first column of the matrix. And I'm defining this to be a new variable. I'm calling it temp. Temporarily, I'm going to use this variable. Now, you might guess already that why I did this here, right? I'm reversing this step by step. Okay, we're done. That's it, right? So you take the column, divide it by the pivot, multiply by the row, subtract it from the original matrix. You zero out kth row and kth column. You can try this in Julia. You get the same answer. This show here means just showing the bottom whatever you're doing, right? When Julia performs the calculation, it shows you that line and the answer. If you want to see what's going on in your code, okay? It's very useful. But in any case, I am defining temp to be M minus C1 times R1. And now, this time, I don't start from the original M. I start from where we left in the previous step, k equals 1. Now k is 2. Step 2. Using the new temp matrix, pick the second column and divide it by the pivot. What is pivot here? Y3. Right. K and K entry of the matrix, K equals 2, right? That's going to be the second element on the diagonal. So pivot is 3. Take the column, divided by 3, we get 0, 1, and 2. Take the row and do nothing. Just keep it. Follow the previous process of multiply C2 by R2 and subtract it from temp. And as expected from last time, we zeroed out the second row and the second column. This is our new temp now, right? We're done. We want to go to the next step. So define this new matrix to be temp. Again, you can do this in Julia, because ultimately you won't do it by hand. This is a simple, non-trivial example. That means if you look at it, you can't tell me. But it's simple enough you do hand calculation. Okay? So that helps a lot understanding the algorithms. So we get the same answer. So we calculated correctly by hand. Step 3. What's pivot in this case? Step 3, right. K is 3, pivot is 29. The third row, third column, the third element on the diagonal. So take the column C3, divided by the pivot, you get 0, 0, and 1. Take the third row, do not change it, multiply C3 by R3, you get basically the same temp matrix back, right? So, and in this step, we recovered the temp at the third step. So if you subtract it, we get 0. The result will be just 0. So basically, temp minus C3 times R3 will be a 3 by 3 matrix of zeros. Okay. Well, it sounds like if we subtracted these things from M, and we can also see that C1 times R1, C2 times R2, plus C3 times R3, which, by the way, we can stack them horizontally and stack them vertically. We can recover M, which is just going backward in whatever we did when we were subtracting, right? This is for verifying the last part. We get all zeros. You should try this in Julia. So from this experience that by going through this algorithm and picking column, dividing it by pivot, picking the row, multiplying them, subtracting from the matrix that we have from the previous step, and the first step is the original matrix itself, we can zero out the entire matrix. That means we are decomposing matrix into this sum that we learned today, right? A bunch of columns times rows and add them up. We can recover the matrix now. So we learned that if we stack C1, C2, C3 or horizontally, right? Remember, this was C1, right? C2 and C3. What do we see?
Just to clarify, are C1, C2, and C3 all the respective columns divided by the respective pivots?
Yeah. Yeah. Yeah, it is. They're not the columns of the original matrix. Yeah, so just, if the notation is confusing, these are columns that we obtained by going through the algorithm, steps that we did, okay? Do you see a pattern here that we have a triangular matrix, lower triangular matrix? When we stack rows vertically, we have an upper triangular matrix.
For the lower triangle, is it always going to be that the diagonals are all 1 since it's divided by?
Because we normalized, right? Because otherwise, if we don't normalize, we are multiplying the diagonal elements twice, right? When we multiply L by U. You can try. That won't give the original matrix. It is just by direct calculation you can verify that. That needs to be done, okay? So we recovered L and U. And M is, in fact, L times U, the product of a lower triangular matrix and an upper triangular matrix. I'm going to construct L and U here in Julia based on C1, C2, and C3. Now, you don't see the code because I had a notebook that I calculated them previously. This is a snapshot of that. So I already have C1, C2, C3, R1, R2, R3. So LU will recover M. We have successfully factorized the matrix into a lower triangular matrix and an upper triangular matrix. Do you have any question so far about the steps that we went through? Okay. Now, in general, if the matrix is very, very large, we can still do the same thing, right? Take the first column, divided by the pivot, the first element on the diagonal, multiplied by the first row. Whenever you do this, what happens when you multiply C and R, this one here will, first of all, will reproduce the first row, okay? Now, because each of the elements of C1 are also divided by A1, 1, right? When you multiply each of them by the first element, it will reproduce the first column of the original matrix, okay? So that's the reason we need that one. And then when you subtract from the original matrix, because they're the same, we just reproduce the first row and the first column. You can zero out that row and column. So that's the logic behind that normalization, because we want to zero out rows and columns step by step until nothing is left. By the time we do that, we have decomposed the matrix into a lower and upper triangular matrix. And because each time as we move forward, we pick the next one to be our column, right? There's always everything above that diagonal element is always zeroed out. So the combination of C's will give you a lower triangular matrix. It's very intuitive to look at it now and imagine it as we move forward. And then when you go and stack rows vertically, right? Everything before the diagonal element is zeroed out or below. Does this make sense? Now, obviously, that we will be in a big trouble if the diagonal element is 0. It's not possible to continue. Next time, if the matrix is not singular, we will learn a trick to get away from this.
What if the what if the values on the like the first when we first did C1 and R1, instead of being a 6, it was like a 5, and you had to divide by 2. What would you do in that case?
You are referring to?
So what happens when the pivot does not divide the C column, into a whole number?
What happens if the pivot does not result into a whole number?
Yeah.
Okay. So that's the question that we have. Now, this will be 1, right, because they're the same number. The question is, what happens if we divide these two, we lose accuracy, and then we multiply them? The result is not these. It's a very good question, because if we divide it and then multiply it and then we subtract it, there is no reason you get exactly 0 in a computer, right? You can try it, because you lose numerical accuracy. That's a good practice for the lab, but I can just tell you that a lot of algorithms try to avoid unnecessary division, right? If we can avoid that, we do that, right? But also, a lot of operations are up to just numerical accuracy, right? And things can go wrong sometimes for special cases. But in general, that's not a problem. We can handle it. And we don't have to literally divide it and then multiply it if we know that that's just what's going to happen, right? We just don't do it. We construct it that way. But I think for floating point numbers, that's not a problem. You can try. It's going to be very close, right? And hopefully that's okay. Maybe you can do a rounding in the end. If it's a tiny, tiny epsilon value, you can zero it, right? Okay, so I just finished with this, that to solve a system, if we have ax equals b, we can factor a. Obviously, we just learned it into lu. We have lu times x equals b. Now, to solve this system, we need 2 steps. Define x times x to be y, right? Here. Then ly equals b, right? So we have 2 systems to solve. So here we solved the first one, ly equals b, using forward substitution. Once we have y, we solve the second equation, for x using back substitution. That's how it works. Okay? We'll talk about it more next time. Besides permutation, I'll have some examples I'll write down for you. These are just for examples. So we will continue LU factorization next time, and we're still in chapter 5. Okay? All right. Thank you, and see you next time.